everyone, welcome to the channel Vidyutयोग. In this video, we'll discuss dynamic programming method of unit commitment by using MATLAB software. So before starting this video, those who are new to this channel, please subscribe the channel. Now in this video, first of all, we'll discuss about concept of the unit commitment, its advantages, limitations. Then we'll discuss one example, and then by using MATLAB software, we'll try to make the simulation for one example. Now, first of all, what is the concept of unit commitment? So, unit commitment is nothing but optimum allocation or commitment of generators or unit at each generating station at various station load level, including load shedding among committed generator. So, first of all, what is the meaning of this? We know that in case of the interconnected system, there is a variation of load on power station from minimum to maximum load level. So whenever there is load changes, at that time we are having the challenge that we need to select the generators among the available generator, and we have to take the care that whatever the commitment, it should be optimum. That means it should be occur at minimum fuel cost. For this, in case of the unit commitment system, we select the optimum allocation or commitment of generator. That means we select the generators or we make the commitment of generators which are optimum and having the less fuel cost. So which generator will be selected among the available generator, that we decide under the concept of unit commitment. So the continuous variation of load on the power system poses a different problem in modern power system operation. Consumers enjoy full facility to operate the load connected to their ends as and when needed. There are many generating units supplying the demand of the consumers. It is not necessary to run all the generators at a time when load reduces or vice versa, and this needs the utility to a strategic thought to the problem. Now, what are the major problems dealing with the planning? First, compare the power generated with the load demand. If the load is large, then decide to which generators are to start. The priority of start procedure has to take into account the economical operation of the station. If the load is less, then to decide as to which generating unit are to shut down, their priority and operational sequence, and this action has to be taken from economical operation of the unit. So computational procedure for making such decision is called as unit commitment, and it is abbreviated as UC. Thus, the unit commitment determine the unit that are to be operated for a particular load and decide which unit should be turned on, the sequence of the operation when the load changes, etc. And an experienced person can make the things more simply by using the thumb rule. Now, what is the importance of the unit commitment in power system? So, economic dispatch provides the strategy to distribute the total load on the power system in most economical way. Then the question that appears is about the necessity of unit commitment. So in unit commitment problem, judicious solution is provided. Plan the base set of units to be operated under different loading condition, predicted or forecasted over a period of time. So need of unit commitment is planned commitment, that is ordered optimized schedule ranging from minimum to minutes to hours. Then for the weekly pattern development, unit commitment is necessary. Then the process of turning on and off the unit, that is the sequential, economical and ordered planning result in saving. And this unit commitment is particularly essential for thermal plant. In other types of the generation, the agreement costs are much smaller. Now, what are the constraints of unit commitment? Constraints means what are the limitations while implementing this unit commitment in practical level. First one, country standard, that is standards are different for different countries. Then we need to consider the safety point. Then we need to follow the design considerations. Then we need to take care about the cost considerations, then performance and operational constraint. That is, operational constraint means it may be the minimum and maximum generation limit of each generator. Now, what are the different methods of unit commitment available in power system? There are mainly four methods. First one, priority list method. Second one, dynamic programming method. Third, method of coordination. And fourth, that is Lagrange's relaxation method. But for this video, we are going to study the dynamic programming method. That is second method of unit commitment. Now, what is the dynamic programming method of unit commitment? Quickly, we will go through the theory and then we'll go start the simulation. So, in case of the dynamic programming method, in a practical problem, the UC table, that is unit commitment table, is to be arrived for complete load cycle. The load is assumed to increase in small but finite size step. Dynamic programming method can be used to advantage for computing the unit commitment table. So in this theory part, actually I have referred the power system analysis by Nagaraj Kotari book, and also for the simulation also we are going to consider the numerical from the same book. So I will suggest you can use this book for the unit commitment concept. Now, in dynamic programming method, it can be used for advantages for computing the unit commitment table, where it is not necessary to solve the coordination equation, while at the same time the unit combinations to be tried are much reduced in number. And for this reason, dynamic programming approach will be advanced here. So the total number of units available here, meaning of unit is nothing but generator. So the total number of units available, their individual cost characteristics, and the load cycle on the station are assumed to be known priority. Further, it shall be assumed that load on each unit or combination of unit changes in suitably small but uniform steps of size. Like del megawatt is equal to 1 megawatt. That means load changes with step size of 1 megawatt. So step size may be 0 megawatt, 1 megawatt, 2 megawatt, 3 megawatt, etc. Starting arbitrarily with any two units, the most economical combination is determined for all discrete load levels of combined output of two units. At each load level, the most economical answer may be to run either the unit or both units with certain load sharing between the two. Now, the most economical cost curve is discrete form for the two unit thus obtained and can be used as the cost curve of single equivalent unit. The third unit is now added and the procedure is repeated to find the cost curve of the three combined units. It may be noted that in this procedure, the operating combinations of the third and first and third and second are not required to work out, resulting in considerably saving in the computational effort. The process is repeated till all the available units are exhausted. So the advantage of this approach is that having obtained the optimal way of loading k unit, it is quite easy to determine the optimal manner of loading k plus 1 unit. So the cost function, which is denoted by the fn of x. What is the meaning of fn of x here? So fn of x is nothing but minimum cost in rupees per hour of generating this bracket value, that is x megawatt by nth unit. Similarly, what is the meaning of fn of y? It is cost of generating y megawatt by the nth unit. Similarly, what is the meaning of fn minus 1 in bracket x minus 1? The minimum cost of generating x minus y megawatt by remaining n minus 1 unit. So don't get confused here. You should have the idea how what is the meaning of this term, and because it is necessary while discussing the example. Now the application of dynamic programming result in the following recursive relation. So what is that recursive relation? Fn of x is equal to minimum of fn of y plus fn minus 1 in bracket x minus y. So using the above recursive relation, we can easily determine the combination of unit yielding minimum operating cost of load ranging in convenient steps from minimum permissible load of smallest unit to the sum of capacities of all available units. In this process, the total minimum operating cost and the load shared by the each unit of the optimal combinations are automatically determined for each load cycle. So the use of dynamic programming method for solving the unit commitment problem is best illustrated by the example. So consider the example system having 4 thermal generating units with parameters listed in table. So that table we'll discuss in the next slide. It is required to determine the most economical unit to be committed for load of 9 megawatt. See, just give attention here because we are going to consider this same example for the simulation purpose. So let the load changes be in the step of 1 megawatt. So here, in short, again I repeat the which numerical statement which we have discussed in the last slide. Here there are total 4 units or 4 thermal power station which are denoted by unit number 1, 2, 3, 4. And each generator is having its constant. Constant means limitations. That is minimum operating capacity and maximum operating capacity. So here the minimum generating capacity of unit number 1 is 1 megawatt and it is maximum, that is 12 megawatt. Similarly, for the second, third and fourth generator, minimum and maximum generating capacity are same. That is minimum generating capacity is 1 megawatt and maximum generating capacity is 12 megawatt. Now the fuel cost equation, the parameters which are needed for the fuel cost equation are shown here. So cost curve parameter D is equal to 0. The parameter A, which is having the unit of rupees per megawatt square, it is 0.77 and 23.5, that is 0.77 megawatt for A parameter for the first unit and B 23.5 for the second unit. Similarly, A and B constant for second, third and fourth generators are shown here. Now, how we'll calculate the F1 of X is equal to small f1 of X because both are having same meaning. What is the meaning of this? The minimum cost for generating X megawatt by first unit. First unit means this is the unit number 1. Here what we have to calculate? We have to calculate the unit commitment for generation of the 9 megawatt. And for that, first of all, we'll calculate the Fn of 9, which is having this meaning small f1 of 9. What is the meaning of this? The minimum fuel cost or the cost for generating 9 megawatt by the first unit. So how it will be calculated? The fuel cost equation is 1 half A1 Pg1 square plus B1 Pg1. Here A1 is nothing but A parameter for the first unit. B1 is nothing but B parameter for the first unit. Pg1 is the cost generated by the power generated by the first unit. So the fuel cost equation is 1 half A1 Pg1 square plus B1 Pg1. So 1 half into A1. A1 is for the first unit is 0.77, that is 0.385 into Pg1, that is for generating 9 megawatt. So into 9 square plus B1. B1 is 23.5 into 9, that is rupees 2.685 per hour. Similarly, by using the fuel cost equation for each generator, and if you are having the idea about how much unit we need to produce or generate, we can easily calculate the fuel cost for that generator. Now, from the recursive relation, computation is made for F2 of 0, that is cost of generating 0 megawatt by the second unit, F2 of 1, that is cost of generating 1 megawatt by the second unit, F2 of 2, that is cost of generating 2 megawatt by the second unit. Similarly, up to the F2 of 9, because maximum limit is 9 megawatt, that is F2 of 9 is cost of generating 9 megawatt by second unit. Now, what is the meaning? How we can calculate the F2 of 9? That is, which generators will be selected and what will be the minimum cost? So, for generating 9 megawatt of power by the 2 units, here 2 is nothing but number of units. 2 units is calculated as minimum of what will be the combination. Suppose we have to generate the power by the 2 units, what will be the combination? That is, first generator will share the second generator will share the load of 0 megawatt, and first generator will share the 9 megawatt. This is the first case. Second case, maybe second generator will share the load of 1 megawatt, and first generator will share the load of 8 megawatt. Third case, maybe second generator will share the load of 2 megawatt, and first generator will share the load of 7 megawatt. Similarly, up to this, there are 9 combinations. That is f2 of 9 plus f1 of 0, f2 of 4 plus f1 of 5. Here we'll calculate the cost for each combination. But in case of the unit commitment, we have to select the combination which is having the minimum cost. And that we have to decide which combination is having the minimum cost in the further steps. So by computing the term by term and comparing the result, if we compare the, now you are having the idea how to calculate the cost of f2 of 0, f1 of 9 from this fuel cost equation and combination. So if we compare this calculation, it is observed that in among this combination, the best combination is f2 of 2 plus f1 of 7. That is, second generator will share the load of 2 megawatt, and first generator will share the load of 7 megawatt, at which the cost is minimum. That's why from the unit commitment table we can say that if we have to select the two generators, then 9 megawatt, for generating the 9 megawatt, we'll use the two generators. Second unit will share the load of 2 megawatt, and first unit will share the load of 7 megawatt. Similarly, we can calculate the f2 of 8, f2 of 7, f2 of 1, f2 of 0, etc. And similarly, we can calculate the f3 of 0 to f3 of 9. Okay, and also we can calculate the f4 of 9. So for the f4 of 9, f4 of 0 plus f3 of 9 is the best combination. That is, suppose if we have to use the, for generating 9 megawatt, if we have to use the first generator only, we can calculate the f2 of 9, sorry, f1 of 9. If two generators are used, we need to use the generator number 2 and generator number 1. If the 9 megawatt we need to share among the three generators, f3 of 9, if third generator we have to use, then the cost is this. If we have to use the fourth generator, then cost is this. Okay, so examination of f1 of 9, f2 of 9, f3 of 9 and f4 of 9 lead to the conclusion that optimum unit are to be committed for 9 megawatt are loads are 1 and 2 sharing the 7 megawatt and 2 megawatt. So this is the optimum allocation. That is, if we have to share the load of 9 megawatt, f2 of will share the load of 2 megawatt, f1 of share, f1 will unit number 1 will share the load of 7 megawatt. That is the optimum allocation or unit commitment. Okay, now here the this unit commitment table is shown for the load sharing from 1 to 5 megawatt, 6 to 13 megawatt, 14 to 18 megawatt, 19 to 48 megawatt. When to 1 to 5 load is available, at that time only first generator will share the load. How we will calculate? We'll calculate the combinations and we'll decide the generator which is having the minimum cost, and from that this table is obtained. So it is called as unit commitment table. That means, suppose I am having the 4 generators which we are discussing in this example, and if the load is changes from 1 megawatt to 48 megawatt, then decision will be taken from this unit commitment table that which generators should be in on condition and which generators should be in off condition. So here 1 represents that the generators will be available for generator. 0, that means those generators will be idle during the or off for particular load. So if the load variation from 1 to 5 megawatt, entire load will be shared by the first generator only. If load variation is from 6 to 13 megawatt, the load will be shared by the first and second generator. If the load is from 14 to 18 megawatt, load will be shared by the first, second and third generator. And if the load variation is from 19 to 48 megawatts, we need to run all the 4 generators. Okay, and this type of the table is called as unit commitment table. So mostly when we are going to implement the unit commitment table, by the history, we have to decide the variation of load among the on the available system, and according to that we need to prepare the unit commitment table. So if the unit commitment table is ready for the any load variation, we can easily take the decision of unit commitment. Okay, now what are the assumptions for this unit commitment method? So first assumption is state consists of an array of units with specified operating unit and the rest are offline. Second assumption, startup cost is independent of time. Third, shutdown cost is assumed to be zero while discussing the unit commitment. And last one, priority order is fixed. These are the assumptions for the unit commitment. What are the advantages of the unit commitment method? First, the dynamic programming method is more efficient while preparing the unit commitment table. Then in dynamic programming method, it is not necessary to solve the coordinate equations. Then by using the branch and bound technique, considerable computational saving can be achieved. That is, if we get the idea, then no need to do the calculation for all the combinations. And in dynamic programming method, it is not necessary to try all combinations since certain combination need not to be tried at all. So these are the advantages. Now I know that still there might be the confusion in students' mind. That is how we have to use that combination, how to calculate the fuel cost. For that, again, for before discussing the main example, we'll discuss second example so that you will get the clear idea about the unit commitment. Now, in this example, what is the statement of the example? Two generating units, G1 and G2, operate a plant to supply 8 megawatt of load. So, what is the load? 8 megawatt. Determine the most economical unit to be committed to a load demand of 8 megawatt. That is, for the 8 megawatt, we have to determine the most economical unit. That means we need to go with the concept of unit commitment. And most economical means which is having the minimum fuel cost. And second one, tabulate UC, that is unit commitment table for step change of 1 megawatt, starting from minimum to maximum. Now, this table gives the information about there are two units, unit number 1 and 2. Unit means generators. What are the constraints or limitations? So the minimum power generated by each unit is 1 megawatt and maximum is 10 megawatt. And regarding the cost curve parameters, the parameter A, B and D for unit number 1 and 2 are shown here. So D parameter is 0 for both the units. Okay, now the cost function in general form is given by the Fi is equal to 1 half AI PGI square plus BI PGI plus DI. For example, for the first generator, if we have to consider, it will be F1 of 1 half A1 PG1 square. A1 is 1 for the first generator. B1 for the first generator is 10 and D1 is 0. Similarly, F2 is equal to 1 half A2 PG2 square plus B2 PG2 plus D2. So A2 for the that is for the second generator A parameter is 2, B2 that is B parameter for the second generator is 15 and D2 that is D parameter for the second generator is 0. Now incremental phase cost is given by DCI DPGI is equal to AI PGI plus BI. Now we'll calculate the cost of generation of power for unit number 1 starting from minimum to maximum capacity. So F1 of 9 we have already discussed, it represents that cost of generation of n megawatt by the unit 1. F2 of n is cost of generation of n megawatt by unit 2. So what will be the cost of generation of 0 megawatt by the first unit? F1 of 0, just put the parameters in this first equation. So here if F1 of 0 means PGI is 0. So the value of the value will be 0. F1 of 1, that is in this equation put Pg1 is equal to 1 and refer the 1 A, B, D parameters for the first generator. So if we put in this equation 1 half into 1 into 1 plus 10 into 1 plus 0, 10.5. Similarly F1 of 2, that is just consider Pg1 is equal to 2 in the above equation. In this equation you will get it is 22. Similarly the cost of generating 3 megawatt by the first unit is 34.5 cost of generating 4 megawatt by the first unit is 48 rupees per hour. Then F1 of 5 is 62.5 up to the F1 of 10, that is cost of generating entire 10 megawatt by the first unit is rupees 150. Now in this case, when only one unit is committed, F1 of x is the minimum cost of generating x megawatt by G1 and is equal to F1 of s. Now suppose we have to calculate the cost of generating of power for the unit number 2, starting from minimum to maximum capacity. In this case, F2 of 0 is equal to, here consider I is equal to 2. So F2 is equal to 1 half A2 Pg2 square plus B2 Pg2 plus D2. A2, B2 and D2 you can refer here. So F2 of 0 is 0. F2 of 1 half into, consider Pg2 is equal to 1 in the equation in the last slide. The 1 half into 2 into 1 plus 15 into 1 plus 0, 16 rupees. Similarly, cost of generating 2 megawatt by the second unit is 34. Cost of generating 3 megawatt by the second unit is 54, up to the cost of generating 10 megawatt by the second generator is 250. So now you are having the cost of generation by the unit 1 and unit 2 for the load from 0 to 10 megawatt. Now step 3, calculate the minimum cost of generating from two units together for the different load. So minimum for generation of 8 megawatt is F2 of 0 plus F1 of 8. For 7 then F2 of 1 plus F1 of 7. What are the combinations? Second generator will share the load of 2, first generator will share the 6, because total load is 8 megawatt we have to consider. Then second generator will share the 3, first generator will 5. Second generator will share the load of 4 megawatt, first generator will share the load of 4 megawatt. That is by for 8 megawatt of load we are having the 9 combination. And if we are having the value of F2 of 0, F1 of 8, we are having the value of F2 of 1, F1 of 7. We are already discussing the step 1 and step 2. Just put those values here, then you will get the total cost. F2 of 0 plus F1 of 8 is 112. F2 of 1 plus F1 of 7 is 110.5. And similarly, you can write values or cost of generation for all combination. And of course, in the unit commitment table, we have to select the combination which is having the minimum operating cost. So from this table, it is observed that the minimum operating cost is 110.5, and it is for the second combination, that is up to 1 plus F1 of 7. That means we can say that if the entire load is 8 megawatt, the best combination is generator 2 will share the load of 1 megawatt and generator will share 1 will share the load of 7 megawatt. Okay. Similarly, we can calculate the for 7 megawatt of load. For 7 megawatt of load, the combination is, the minimum cost combination is okay. For the second, that is 7 megawatt, the minimum cost is 94. That is for this combination. Similarly, we can calculate the F2 of 6, F2 of 5, etc. And from the unit commitment table, it is observed that for these two units, if the load is from 1 to 6 megawatt, only first generator one will share the load. And if the load change is from 7 to 20 megawatt, then both the units or both the generators need to start. So this is the unit commitment table. So now I think it is clear that what is the dynamic programming method for unit commitment, then how we need to do the calculation, and what are the constraints, what are the advantages of this method. Now actually we'll go with the our experimental part, that is title is development of dynamic programming method of unit commitment. We have to study this method by using the MATLAB software, and apparatus is of course MATLAB software. Theory, whatever I have added here, we have already discussed, and we have to solve one numerical by using the MATLAB software. So that numerical also we have discussed initially, that is, this is the table That is, in case of this numerical, there are four generators, unit number 1, 2, 3, 4. If you remember, we have already discussed in this video only. Then minimum and maximum, that is constants for the each unit is 1 megawatt and 12 megawatt. And A and B parameters are given here. We have to calculate the load for sharing the 9 megawatt of load. So from the theoretical calculation, we have observed that the answer is the 9 megawatt load will be shared by the unit number 1 and 2. That is, in these two units, unit 1 will share the load of 7 megawatt and unit 2 will share the load of 2 megawatt. So same program, same numerical will simulate with the help of the MATLAB software. So for that, I have opened this M file. I will try to upload this M file in this video description also, so that you can easily download it and you can run this simulation from your side. So by the time I have opened this file. So this is the MATLAB program for the optimal unit commitment by dynamic programming method. And numerical is from the Nagraj Kothari book only. So those who want to study this concept, you can refer the Nagraj Kothari book and you can run this program and you can study the concept of unit commitment, that is dynamic programming method for unit commitment. Now here constant alpha is value, those values are actually given in the numerical. Here these are the values 0 0.77, 23.1.602, 2.5 A and P values. So here it is represented by the, in case of the program, it is denoted by alpha means A, beta means B parameter, PG minimum, that is minimum generating capacity of each unit 1111, PG max, maximum generating unit capacity of the each unit, that is 12 megawatt, and N is equal to 9. That is, we have to decide the optimal allocation or unit commitment if the load shared by the generators is 9 megawatt, that is N is equal to 9. And this is the MATLAB program to run this simulation. Okay, so if I run this program, then you will get the output in the workspace. See here, alpha parameters are given, beta parameters are given, cost is 0. C unit, what is the meaning of C unit? That is, here I have explained the meaning of C unit in this at the end of this example, that is simulation result. C unit is nothing but it will display the number of committed units on each of the four generators. That is, if C unit for a particular generator is 0, it means unit is not committed. That is, that generator is in off condition. And C unit is having particular value, that means that much value of load is shared by the generator. So the total number of units to be committed are here C unit for the 9 megawatt of load. Here C unit is 7200. That means first generator will share the load of 7 megawatt, second generator will share the load of 2 megawatt, third generator will share the load of 0, and fourth generator will share the load of 0 megawatt. That means the answer is similar to our theoretical calculation. Through the theory also we have observed that for 9 megawatt of load, among the available four generators, first and second generator will share the load, and in which first generator will share the load of 7 megawatt and second generator will share the load of 2 megawatt. And the same we have obtained by the simulation also. So I hope the concept is clear. So again I repeat, in this method we have discussed about the concept of unit commitment, then different methods for unit commitment, then we'll try to understand the dynamic programming method of unit commitment in detail, and the numerical from the Nagraj Kothari book we have simulated with the help of the MATLAB software. So I hope this video is helpful for you. I again request those who are new to this channel, you can subscribe the channel, and also you can go through the other videos which are available on this channel with Vidityo. Thank you all of you.